All right, my friends, welcome back. Now, in the last video, we talked about polar form and what polar points and equations look like. And of course, the obvious question you had is, that's great, how do I take a derivative of these jumps? Well, there are a lot of different derivatives you could take because we have a lot of variables, right? We have r, theta, x, and y. And my goal today is to talk to you about some of those derivatives. All right, so let's talk about the most basic derivative. If you have function r in terms of theta, like the one we had in the last video, r equals 2 plus 2 sine of theta, what does the derivative dr d theta represent? I mean, finding that, of course, is really straightforward, right? That's just derivative to 0. That's just 2 cosine theta. So what that is the change in r, which, remember, we want to represent as the distance from the origin as theta increases. That's how you want to represent that. So, for example, like what this graph looked like, if you graphed like this r equals 2 plus 2 sine theta, we remember that graph made what was basically like an upside down heart type thing. It looks something like that. Now, if you plug in a couple points, so if you plug in, for example, pi over 4, if you plug in pi over 4, you get a dr d theta equals 2 times cosine of pi over 4, which just ends up being 2 rad 2 over 2, which is just square root 2. Okay, but what this means is because this dr d theta is positive, what that means is that r, that distance from the origin, is increasing. Or we are moving away from the origin as we go around the curve. So that's saying, as we go around the curve here at pi over 4, like you can see, the graph is getting longer, right? If we look at the distance from the origin, this r, that r value is getting bigger as theta is increasing. But we see kind of, okay, well, I drew my picture poorly, but we see the opposite, right? As we approach somewhere like, say, at pi. Because if we look at pi, we can see as we're going around the curve, that r is getting smaller because the curve itself is getting closer to the origin. So if we look at pi, that dr d theta is equal to 2 cosine of pi, which is negative 2. So what that means is the distance from the origin is decreasing. We're getting closer to the origin. So that's the meaning of this dr d theta. It's just talking about kind of a distance from the origin, whether getting closer or further. And one thing to remember is that theta always goes counterclockwise. Just thinking about how we're measuring angles, we're always like starting at 0 and then going around in the counterclockwise direction. Okay, so let's talk about some other ones. So some other ones say dx d theta and dy d theta. So those are our next kind of derivatives that we're going to begin with. So what those are is that is the change in x. So that's like our horizontal change as theta changes. And then the dx d theta would be our change in y, which of course is vertical, as theta changes. So on a graph, what this would look like say we have this same graph. If we were to like see, the graph looks like that. If I were to look at this point right here, like as I go around the curve, I'm going in that direction. So I am moving up, and then I'm also moving left. So if I'm moving up, that would mean that my dy d theta would be a negative number. If I was moving left, that would mean my moving up would be y is increasing, not decreasing. If I was moving left, that would mean my dx d theta would be a negative number because it's moving to the left. If I were to look like at another point, say down here, like at this point in black here, there I'm moving down and to the right. So if I'm moving to the right, that means my dx d theta would be positive, and that means that my dy d theta would be a negative because my y is decreasing. So that's what dx d theta and dy d theta represent. So the way you're going to find these, so to find these, we're going to start with the equations that we came up with in the last video. So x equals r cos theta and y equals r sine theta. And then we'll take a derivative. So let's give just a quick example here. So suppose we have r equals 3 cosine of theta. And I'm going to ask you to find dx d theta and dy d theta. Okay, so just for an example here, Well, I'm going to start with this equation. So I'm going to start with x equals r cosine theta. And then what we're going to do from this point is we're going to plug in our equation for r. So we're going to take this equation right here and plug it in right there. So that's saying x equals 3 cos theta times cosine theta, also known as 3 cosine squared theta. And then we'll go ahead and take a derivative. Now, obviously from here, the derivative is pretty straightforward, right? Because once you have an equation for x in terms of theta, this is a derivative like you've done all year. This is like 3 times cosine of theta squared. So when we take a derivative, 2 comes down, so it's like 6 times cosine theta to the first power times negative sine theta, which you could write as negative 6 cosine theta sine theta. Okay. Now, if you want to find the dy d theta, we're going to do the same thing, right? I'm going to start with the equation from yesterday, y is r sine theta, and then plug in for r. So y is 3 sine theta. Oh, geez, that's the wrong r. I'm stupid. So y is 3 cosine theta times the sine theta. So I just plugged in for the r right there. And then when I take the derivative here, I just have to use the product rule. I use the chain rule on the dx. Now I use the product rule. So 3 cosine times sine. So that's 3 cosine theta times derivative of sine theta is cosine theta plus the second sine theta times negative 3 sine theta. So if you want to be a good little boy, you can write this as like 3 cosine squared theta minus 3 sine squared theta, or like 3 cosine 2 theta, or however you want to write it. This is fine. Okay, so that's how you take the dx d theta and the dy d theta, and that's what they represent. They just represent like, are we moving to the left? Oops. Are we moving to the left or to the right? So this is movement on the left-right axis, and then the dy d theta just asks whether you're moving up or down. Okay, now the next thing we want to talk about, slope. Slope. And this should be familiar because the slope of the dy dx is exactly what you do in parametric form. You just find the dy d theta and you divide by the dx d theta. Okay, so in this case, like what we just had is the dy d theta, so over the dx d theta here, like for this example, I would just do 3 cos squared theta minus 3 sine squared theta over negative 6 cos theta sine theta. So again, you just find the dx d theta and the dy d theta using what we just did, and then make a fraction. Okay. So that's how you go about and actually finding the slope of something. So if we want to write like, I don't know, a tangent line, let's say a tangent line to r equals 4 sine theta at theta equals pi over 3. This is like an example, something you'll see on the AP test. So just like any time you have to write a tangent line to a curve, you need to come up with like, okay, what is the point? At that point, what is the x and what is the y? And then what is the slope at that point? Because r and theta, like our tangent line, is going to be in terms of x and y. And I guess I should have been clear about that, and the problem will be. But you're going to write the tangent line in terms of x and y. Okay, so if I know, for example, that my x is r cosine of theta, then that means that my x is 4 sine theta times cosine theta. And if my y is r sine theta, and you see how important those equations are for these derivatives, that means my y is 4 sine squared theta. Okay, so then that means that my dy d theta here is just 8 sine theta times cosine theta. The 2 comes down. Here my dx d theta is equal to, okay, so 4 sine theta, derivative of cosine is negative sine theta, plus, and then it just turns out to be 4 cos squared theta. Okay, so if we want to find the point, I kind of did some of this work here, but if I want to find the point, I just need to use like these values here. So the x value there, so x is 4 times sine pi over 3 times cosine pi over 3. So that's 4 times root 3 over 2 times 1 over 2. So that worked out really nicely because this just turns out to be 4 rad 3 over 4, which is just square root 3. Whereas here my y is just 4 times sine squared of pi over 3. And the sine of pi over 3 is, that's root 3 over 2, gross. Wait, is it? I feel like I screwed this up. No, that sounds right. Okay. So the sine of pi over 3 is root 3 over 2 squared. So that's just 4 times 3 over 4, which is just 3. Okay. Cool. So if that's my point, and again, I just use the x and the y equations to find the point, I know it's going to be like y minus 3 equals some slope times x minus pi over 3, x minus root 3, excuse me. And then for the slope of my tangent line is a dy dx. Okay, so I'll just go back, I'll use a different color, purple, and I already found those, right? So I know my dy dx is 8 sine theta cos theta divided by negative 4 sine squared theta plus 4 cos squared theta. So when I plug in this value, pi over 3, you realize these problems take a little while. This is like 8 times rad 3 over 2 times 1 over 2. It's all going to simplify nicely. Minus 4 times rad 3 over 2 squared plus 4 times 1/2 squared. All right, so this just turns out to be 2 rad 3 divided by, okay, so here the root 3 is 3 over 4, so that's like negative 3 plus 1. So it's just like 2 rad 3 over negative 2. Man, that worked out so well. It's just negative square root 3. Anyway, don't worry too much about the simplification. Obviously, you got to know your unit circle for this stuff. But the general strategy there is just using the dy dx. The only other thing I wanted to share with you today is what happens if we have a horizontal tangent and a vertical tangent. And these cases are going to be the same as what we saw in parametric. So if you have a horizontal tangent, again, draw the picture in your head. What does that look like? That means that your dy dx equals 0. And if you have a fraction that's equal to 0, that means the top is 0. So that means your dy d theta is 0. If you have a vertical tangent, that means your dy dx is undefined, meaning it is something divided by 0. So that means the bottom is 0, so your dx d theta equals 0. Okay. And if you have to solve this equation, so for example, like the problem we just had was r equals 4 sine of theta. If you want to see where are the horizontal tangents, okay, so horizontal tangents to that would be, okay, where is my dy d theta equal to 0? Now this is a problem we just did, so let's just use that. So that would be like, okay, this is my dy d theta here. So that's saying that 8 sine theta times cosine theta equals 0. Now, you already solved problems like this last year. We've done them earlier this year, too. You just set the first part equals 0. The 8 does nothing, right? So either sine theta equals 0 or cosine of theta equals 0. So where does sine equal 0? That happens at like 0 or pi or 2 pi. Cosine equals 0. That means the x-coordinate is 0, so the top and the bottom. So that happens at pi over 2 or 3 pi over 2, and so forth. Okay, so that's kind of what's going on with some of these derivatives. That's horizontal and vertical tangent. Vertical is just, of course, dx d theta is 0, same thing. But that's your slope, your dr d theta, your dx d theta, dy d theta. Those are just some of the derivatives that we talked about in this video. Okay, bring some questions to class. Thanks for watching, guys.